Hi everybody, my name's Axton. I'm a graduate student at the University of Florida, and I'm a part of the Nonlinear Controls and Robotics lab under Dr. Warren Dixon. Today I'll be talking about a paper called Zeroing Control Barrier Functions for Safe Volitional Pedaling in a Motorized Cycle. This talk will be about the design of a control system for a rehabilitative cycling program meant to treat patients with neuromuscular disorders. Neuromuscular disorders are debilitating conditions that have severe consequences for a patient's health and social life. Motorized rehabilitative cycling is an effective form of therapy for these disorders. By motorized rehabilitative cycling, we refer to a bicycle or tricycle where the rider is able to pedal while receiving assistance from an electric motor. In particular, greater physiological benefits are attained when the rider is able to pedal of their own volition without interference from the electric motor. Motivated to develop a controller that encourages volitional effort from the rider, we define the control objective as follows. The electric motor, rather than regulating the cadence to some set point, will be responsible for constraining the cadence within a user-defined range of values. For example, 40 to 50 RPM. Which would be denoted by the orange lines in this figure. At the same time, the rider will be responsible for maintaining their cadence at the center of the range. Therefore, the electric motor should be inactive at the center of the range, with gradually increasing control effort as we approach the boundary of the range. And it turns out that a design tool called barrier functions provide unique insights into this problem, as we'll see subsequently. On the right, we see past work from our group with a similar control objective. The controller in this work was inactive on the entire interior of the safe range, while there was a discontinuous jump in control effort on the boundary of the range. The disadvantage of this approach is that it results in abrupt control action. A contribution of the current work is that we design a continuous controller using a systematic approach. Here we see a dynamic model of the cycle rider system. The dynamic model is an Euler-Lagrange system relating the angular acceleration q double dot to the angular position q and the angular velocity q dot. Some key terms are the viscoelastic tissue torques, disturbances from the cycle and rider, and the input torque, which consists of both volitional effort from the rider and the torque from the electric motor. We don't assume that any of these terms are known, but we do assume that there are known bounds on them. And at the bottom, we write the system in state space form to facilitate comparison with the subsequently explored theory. And something to note about this model is that there's one control input, the electric motor torque, and we treat the volitional effort as a disturbance. The tool that will allow us to develop a controller for the cycling system is a zeroing control barrier function. ZCBFs have been popularized for designing controllers that render a set of states forward invariant, meaning that trajectories starting within the set stay in the set for all of time. And a ZCBF is a smooth function h that defines a safe set, S, as the set of states where the barrier function is less than or equal to 0. The function h is a ZCBF if there exists a set D with S a subset of D, and an extended class kappa function alpha such that this inequality holds for all states and all time. This inequality resembles the Apanov type inequalities, which are common in nonlinear control design. What this inequality says is that for each state, there exists a control input, tau e, such that this quantity is upper bounded by some function of h. And to really quickly make the connection, the simplest example of an extended class kappa function alpha is a function that's linear in h. Now, along trajectories of the system, this quantity becomes the time derivative of h dot, And so the intention is to design our controller so that h dot is upper bounded like so. What this inequality says is that when h is positive, meaning the state is outside of the safe set, we require h dot to be negative, meaning that h is decreasing, meaning that the state is moving towards the safe set. So that's a fairly common idea in Lyapunov-based control design. The novel idea that has been introduced with ZCBFs is that when h is negative, meaning the state is safe, we allow h dot to be positive, which means that h is allowed to increase, meaning that the state is allowed to move towards the boundary of the safe set. And what that does is it essentially gives us more freedom in selecting our control input. When the closed-loop dynamics satisfy such an inequality, the safe set is rendered not only forward invariant, but uniformly globally asymptotically stable, meaning that trajectories starting outside of the safe set are guided into the safe set and remain there for all of time. And in Corollary 1 of the paper, we outline sufficient conditions for this to be the case. And Corollary 1 is a minor extension of results available in this work. Next, we use ZCBFs to design a controller for the cycling system in a systematic way. The first step is to encode the control objective. We define a tracking error E as the difference between some user-defined desired cadence Z2D and the measured cadence Z2. Then we define a barrier function candidate H as seen here, and H is formulated such that H is less than or equal to 0 whenever the tracking error E is less than or equal to delta D, where delta D is another user-selected parameter denoting the size of the desired cadence range. So this barrier function H encodes this safe set S, and the control objective is now to render the set S asymptotically stable. And as a reminder, the control effort should be minimal so that the electric motor is inactive when the tracking error is small, i.e. the tracking error is not near the boundary of the safe set. And as a note, we include the mass term M in the barrier function H in order to compensate for some problematic terms in the dynamics. Now, the idea is to use this inequality from the definition of a ZCBF to educate how we select the control input tau E. If the terms F and G from the system dynamics were known, which is a common assumption in barrier function-based control designs, then we can immediately implement this inequality in, for example, a quadratic program, in order to select an appropriate control input. A contribution of this work is that we consider the case where the dynamics are unknown, including the mass term M, which appears in the barrier function itself. In this work, we use robust control techniques to compensate for the unknown terms. Using properties of the dynamic model, we find that this term representing the dynamics of the system is upper bounded for sufficiently large control gains k1 through k3 by this function h bar k. To compensate for the unknown mass term in the barrier function, we define a substitute barrier function hs, which is essentially h without the mass term, and we show that there exists a class kappa function alpha such that the negative of hs is upper bounded by the negative of alpha h. What these bounds tell us is that any control input tau e that satisfies our developed known inequality also satisfies the unknown barrier inequality. Therefore, by implementing the developed inequality as a constraint in a quadratic program, we obtain a controller that renders the safe set asymptotically stable. Furthermore, by minimizing the square of the control input, we also accomplish the secondary objective, which is to choose small control inputs, or the control input 0, whenever the tracking error is small. And we'll gain some more insight on how that happens subsequently. Unfortunately, it's not immediately clear that the quadratic program has a solution for every possible state. Here, we'll address a feasibility issue, which is very closely related to the question of existence of a control barrier function. By inspection of our inequality, we see that if E is equal to 0 and h bar k plus hs are greater than 0, then there's obviously no solution to this inequality. The converse of that statement is that if hs plus h bar k are less than or equal to 0, then the inequality 19 is satisfied by choosing tau e equal to 0. Therefore, the problem when E is equal to 0 is addressed simply by requiring that hs plus h bar k, when E is equal to 0, are less than 0. Since these functions depend on user-selected parameters, it's well within our power to make this inequality true. I'll also emphasize that because the functions hs and h bar k are continuous, by enforcing a strict inequality when E is equal to 0, we ensure that there's a neighborhood about the point E equal to 0 for which the functions are still negative, and consequently tau E equal to 0 remains an admissible control input. Following from the development on the previous slide, we design a controller such that when this function hs plus h bar k is less than or equal to 0, then the control input is set equal to 0. Otherwise, tau e is set equal to this function, tau con of e. The first thing to notice is that the controller only depends on the functions hs and h bar k, which, if you recall, are functions that are defined in terms of constant user-selected parameters. Therefore, the controller can be implemented online. On the left, we see a plot of the control input for various selections of the tunable parameters. What this plot shows is essentially that the control input is accomplishing exactly what we want in terms of the control objective of the system. First of all, the feasibility condition that we've developed guarantees that there is a neighborhood about the point E equal to 0 where the control input is equal to 0. Consequently, the rider is forced to pedal of their own volition in order to maintain the tracking error near the cadence set point E equal to 0. At the same time, we see that the controller is a continuous function which smoothly ramps up to some non-zero value on the boundary of the safe set, denoted by these dashed lines. And that value is essentially a value that's sufficient to maintain the cadence within the user-defined bounds. Formally, we say that given the feasibility condition, the developed controller solves this quadratic program, which we saw on a previous slide. Furthermore, the controller is locally Lipschitz continuous on the entire state space, and this statement that there exists a neighborhood about the point E equal to 0 such that tau E is equal to 0, in simple terms, says that there is no dividing by 0 in the controller. To recap, we designed a controller that enforces that the function h is a ZCBF. From there, we go on to show that the safe set S is uniformly globally asymptotically stable for the closed loop system. We've already discussed these gain conditions, where the first is the feasibility condition, and the second just says that there are some theoretical constants for which the control gains in the function h bar k should be selected sufficiently large. A sketch of the proof. From the previous discussion, we've already established that h is a ZCBF. It follows quickly from there that some boundedness properties of trajectories to the system. We then have to take the additional step of showing that maximal solutions are complete, and this is because the safe set S is not compact in R2. After establishing that, we conclude that the safe set is uniformly globally asymptotically stable. Finally, we conducted an experiment to demonstrate the controller where an able-bodied rider pedaled the bicycle while viewing their cadence on a screen. In the top image, we see the rider's cadence, and in the bottom image, we see the current input to the cycle's electric motor. The dashed lines indicate the boundaries of the desired cadence range set by the parameter delta D. The thick red lines indicate times at which the rider was asked to change their objective when pedaling the cycle. The first phase of the experiment consisted of the rider pedaling of their own volition and trying to maintain their cadence within the user-defined range. For this phase, the motor control input was virtually zero, where we see a slight offset due to EMF from the electric motor. In the second phase, the rider was asked to stop all volitional efforts and let the motor maintain their cadence within the user-defined range, which we see was successful. And in the last phase, the motor was asked to pedal harder than they normally would, with just enough effort to feel some resistance from the electric motor. As we see, the electric motor was also able to constrain the cadence within the range for this case. In summary, the controller is inactive when the rider's volitional efforts are sufficient to meet the tracking objective, while still constraining the rider's cadence within a user-defined range. Future experiments will investigate the controller in a more realistic rehabilitative scenario to investigate whether the controller is truly effective at encouraging significant volitional efforts from the rider. That's the end of the talk. Thanks for listening. Moving forward, we'll be introducing functional electrical stimulation into the control system to further increase its rehabilitative potential. This is an area that our lab has many years of experience in. Additionally, further experiments will be conducted, including patients with neuromuscular disorders. Again, thanks for listening, and let me know if you have any questions.